Hey guys, this video is from section 11.2, which is about areas of regular polygons. We're going to just start off by finding the area of equilateral triangles. So remember the formula for area of a triangle, 1/2 base times height. Or if you prefer this way, you could also do base times height divided by 2, means the same thing. It's up to you. Okay, so first of all, we know this is an equilateral triangle because all the side lengths are marked as congruent. That means that each of these angles are 60 degrees, right? Okay, that's important to note, as well as, all of these sides are going to be 10. So my base is equal to 10, I just need to find my height. And the way that you're going to find that height is just like we did with those problems where you drop the altitude. This is your height right here, this side segment that we just drew in. Okay, so really what you just have created is a special right triangle, a 30, 60, 90 with a hypotenuse of 10. And according to our special right triangle rules, we know that the short leg is half of the hypotenuse and the long leg is the short leg times √3. So really we have a height of 5 times the square root of 3. So now I could find my area of this triangle, the base, which is 10, times the height, 5 √3, all divided by 2. So the area of this triangle would be 50 √3 over 2, which simplifies to be 25 times √3. Now, it's important to make sure you include units. Since this problem didn't really have inches or centimeters, we just write the word units squared because area of any shape is always squared. Take a second to jot down these two equilateral triangles and the information that goes with it. This one has a side length of 8 inches. This one has a height of 7 √3 centimeters. See if you can go through, find the area of them, and then resume the video when you're ready to check your answers. Okay, so again, when solving for the area of an equilateral triangle, really what you need to do is draw in that height if it's not there for you already. Okay, calculate that height using your special right triangle relationships because you know an equilateral triangle is going to have 60-degree angles and that height's going to make 90 degrees. So then you're going to have your special 30, 60, 90. Okay? And then once you have all that information, you simply plug it right into the formula base times height divided by 2. Okay? Okay, let's try a couple examples for regular hexagons. Remember that is a 6-sided polygon, and if it's regular that means all the side lengths are the same. That's why I have tick marks here. And we also know that all of these angles on the inside, these are called central angles because they are connected to the center. That's what this orange point here is. We know that all of those central angles will be the same because all of these side lengths on the hexagon are the same. Okay, so if we test this, 360 divided by 6, all of these central angles are 60 degrees. Right? Now, if we wanted to, we could use what we learned in the past to solve for one interior angle. One interior angle of a hexagon. Remember, that's our formula, n minus 2 times 180 divided by n. And in this case, if it's a hexagon, n is 6. So 6 minus 2 is 4. 4 times 180 divided by 6. Whoops. And this comes out to be 120 degrees. So what this basically means is that this angle, one interior angle for this whole hexagon is 120 degrees. Well, if I split that in half, it will give me each individual angle from these triangles. So 120 divided by 2 is 60. Well, there you go. I've got 60 degrees on the inside, 60 degrees here, and 60 degrees here. So therefore, we just showed that a hexagon, a regular hexagon, forms 6 equilateral triangles. Now, we just learned how to find the area of an equilateral triangle. So if you can find the area of an equilateral triangle, you can now find the area of a regular hexagon, because all you have to do is take that area of the triangle and then multiply it by 6. Okay? Okay, here are a few examples. So first one has a distance of 20 from the center to this vertex. So if you want, you can redraw this triangle off separately if you need to do that. This equilateral triangle here. Remember, you always need to find the height in order to use the formula. So again, this is a 60-degree angle. So we have a 30, 60, 90 again. And if the hypotenuse of that triangle is 20, the short leg is 10, and the long leg is 10 root 3. So the area of this triangle is the base, which is the whole bottom side, 20, times the height, 10 root 3, all divided by 2. So now I'm going to simplify this. The area of the triangle is 100 times the square root of 3 units squared. Again, that's just the area of this one little triangle. I want to know the area of the whole hexagon. So now I need to decide how many triangles there are total, which you can either count them or know in a hexagon there will be 6. So the area of the hexagon is equal to 6 times the area of my triangle, which we just figured out is 100 root 3. So my final answer, 600 root 3 units squared. That's the area of my whole hexagon. Okay, see if you can try part B. Now in this one, they give you the height. The height is equal to 2 times the square root of 3. So see if you could use that height to find the area of one triangle, and then multiply by 6 to get the whole hexagon. And here's your answer so that you can check, make sure that you did this correctly. It's kind of like backwards from this one, because in this example they gave you the base and you had to find the height. In this example they gave you the height, which really we know it's like the long leg, right? In a 30, 60, 90, if you have the height, that's really the long leg. So the short leg is 2, which means this whole side is 4. Okay? Go ahead to a fresh page and we will try finding some areas for other types of regular polygons besides hexagons. Okay, so example 3, finding area of other regular polygons. I'm going to start off with a pentagon. Remember, that means that we have 5 sides. Your first step is to find half of one interior angle, just like we did for a hexagon. Remember, it came out to be 60, but in this case, it's going to be something else. So I'm going to have 5 minus 2 times 180 divided by 5. I'm getting 108. 108 is like a whole interior angle. I only want this, half of it. So I need to cut it in half, or half of that. Oops. Half of 108 comes out to be 54 degrees. So that means this is 54 degrees. Okay, now we need to calculate the height of the triangle. And the triangle that I'm talking about is this whole triangle. So if you need to, draw it off separately. Right? We've got side lengths here of 1, and we have a 54-degree angle. And I have h. How am I going to find h? Well, you're going to need to use SOHCAHTOA. Because this is not a special right triangle, the only way to find this side is by using your trigonometric ratios. Okay, so then you're going to do what we did on the very last quiz. Relative to this angle of 54 degrees, we have the opposite leg and the hypotenuse. So opposite and hypotenuse means you need to use sine. And then you set it up. Sine of 54 equals opposite over hypotenuse. And then you can solve from here. Multiplying both sides by 1 is not really going to do anything, but if it was any other number, you definitely need to go through that step. Okay, so basically you're going to type sine of 54. Okay, a couple of reminders when you're using your calculator. Make sure you're always on degrees. Okay. And then we get that the sine of 54 is about 0.8. So our height for this triangle is about 0.8. Okay, now we need to find the base of this triangle, because remember, in order to find the area, I need to have the base and the height. Okay, so now I need to find the base, which is this whole side here. Well, if I could find one piece, I'm just going to label this as x. If I can find x, I know that this side is also x. Then I can find the whole base. Okay, so again, I'm still using this right triangle, 0.8, 1, and this angle 54 degrees. Okay, so now I need to find x. Well, relative to 54, this is the adjacent leg and the hypotenuse. Adjacent and hypotenuse means I'm using cosine. So cosine of 54 equals x over 1. Okay, so then I go to my calculator, cosine of 54, 0.6, about 0.6. Okay, so I'm going to multiply by 2 so that I can have the entire base, and the entire base is going to be about 1.2. Okay, so now that I've got my base and I already figured out my height is 0.8, all I need to do is plug it into the formula to find the area of the triangle. Right, base times height divided by 2, I get 0.48 units squared. Now to find the area of the pentagon, I need to remember, how many triangles were inside this pentagon. Well, if I go back to my original picture, 1, 2, 3, 4, 5 of those big triangles were a part of this pentagon. So really I'm going to do 5 times 0.48, and the area of this pentagon is about 2.4 units squared. Okay, and that's pretty much it. Well, let's take a look at what the heck did we just do. So we found the area of one triangle, and the way that we found that area is by using SOHCAHTOA, because I needed to solve for the height and for the base. And once I had that area, I multiplied it by 5. Okay, so I'm going to show you a shorter way to find a new formula that might be a lot shorter. Okay, so the area of this pentagon, we just did 5 times the area of our triangle. And we know the area of the triangle is the base times the height divided by 2. Okay, now 5 times the base. Well, on my pentagon, each one of these sides was kind of like the base of that triangle, right? This is the base of that triangle. And if it's a regular pentagon, all of these sides are the same thing as the base. So 5 times the base, this is the same as the perimeter for this whole pentagon, right? So I'm going to put that at the end, h divided by 2 times perimeter. Capital P stands for perimeter. Okay, so when we replace that with the perimeter, then I have height divided by 2. Well, what was that height? The height of the triangle? This has a fancy name for any polygon, and it's called the apothem. Okay, so height of the triangle is basically the same as the apothem of the polygon. So this formula is going to become very helpful as we move forward with this unit, 1/2 AP.